Is our world unique? Is Earth an exceptional planet, evolving in an atypical system? Just 25 years ago, it was absolutely impossible to answer these questions. Unless you're completely megalomaniacal, you need to compare yourself to others to know if you're exceptional. But until the end of the last century, we were technically unable to discover planets orbiting stars other than our own. But since then, things have changed a lot. At the time I'm recording this episode, we know of about 5,630 planets in 4,200 planetary systems outside our solar system. For the first time in history, we have enough data before our telescopes to compare ourselves to others. So, how special is our solar system? To answer this question, we need to ask what proportion of the thousands of other recently discovered systems are similar to ours. But before anything else, and just to refresh our memory, let's briefly recall the main characteristics of our solar system. Here you have the 8 planets represented. Near the Sun, there are 4 rocky planets called the terrestrial planets, and farther out, 4 gas giants, which are much more massive and imposing. You can see the inner planets' masses are negligible compared to those farther from the Sun. The ice giants Uranus and Neptune are each about 4 times wider than Earth and 15 times heavier, while Saturn and Jupiter tip the scales at 95 times and 320 times heavier than our planet, respectively. And if we put the Sun to scale, it wouldn't even fit in the picture. Obviously, space is vast. So vast that it's impossible to represent both the sizes of the planets and the distances between them to scale on the same image. So let's stretch all of this out to get an idea of the staggering distances that separate the planets from each other. Let's ignore size ratios and focus on distances. You can now see on the screen the dizzying distances that separate the orbits of the planets from the Sun, as well as their respective shapes. In this type of representation, the planets in our star are not shown to scale. We have 4 rocky planets and 4 gas planets arranged like this. Up to this point, if you're interested in Lis space, it's likely that nothing here surprises you. We're used to our system, and we might even be tempted to imagine its usual shape. And here's where it gets strange. When we point our telescopes to study planets orbiting stars other than our own, we find that this configuration is absolutely not what we see. In fact, the vast majority of the thousands of other planetary systems discovered over the past 30 years are extremely different from ours. You'll see, it's interesting. Already, give or take, about half of the stars studied have systems that are much more compact and tightly packed than ours. Just like the Kepler-11 system, where they've discovered planets orbiting a star similar to our Sun. 6 planets orbit the star, with 5 so close they could all fit inside Mercury's orbit in our solar system. Inside Mercury's orbit? And then, in nearly 1 out of every 2 systems, we find a super-Earth or mini-Neptune-type planet. These are a new kind of planet that we don't find at all in our own solar system. They can be 1.5 to 3 times larger and 2 to 10 times heavier than Earth. They are an intermediate between rocky planets like ours and icy gas giants such as Uranus and Neptune. Not to mention that 10% of the systems studied also have gas giants like Jupiter, extremely close to their star. Lastly, another thing that puzzled us about this diversity is the planet's order. Because the kind of configuration our system has, with 4 rocky planets orbiting close to the star, followed by 4 gas planets that are relatively far away, is what we imagined we would find almost everywhere in the cosmos. But that's absolutely not the case. The vast majority of the systems studied have completely different architectures from one another. See, sometimes we do find systems in which the mass of the planets tends to increase with distance from the star, with the smallest planets inside and the largest farther out. But those in which it's the opposite, where the mass of the planets decreases with distance from the star, seem just as numerous. And we've also discovered systems with rather crazy architectures, where planets of very different masses follow one another with no apparent logic. And then above all, nearly 80% of systems alongside this astonishing distribution of planets. What struck us even more were the shapes, their orbits, because in our solar system, all the planets have orbits that are more or less circular. But in almost all of the thousands of other planetary systems we've discovered, we find planets with strongly marked elliptical orbits. Compared to thousands of other discovered planetary systems, ours has small planets near the Sun and larger ones farther out, with no super-Earths or mini-Neptunes closer to the Sun than Mercury. Mercury would almost seem exceptional. And the first reaction that one might have in the face of this apparent oddity could be to imagine that we are a special system that has something a bit abnormal. Except that if we take a step back, we realize that there is a huge bias here, because these portraits are far from complete. Given that we are not always able to detect all the planets present within systems, due to the detection limits of our current technologies, we always discover what we are able to perceive. Many of them, too small or orbiting too far from their star, go under the radar, and these 5,630 discovered planets therefore only partially reflect the real diversity of system architectures. To convince you, I'm going to show you an image, a scatter plot. Don't run away, you'll see. It's absolutely fascinating. After that, you should spend your life looking at the sky differently. In this image, you will gradually see all the planets that we have discovered over the past 3 decades appear, and we'll be able to compare them to Jupiter, Saturn, Uranus, Neptune, Earth, and Venus. Each dot represents a world, classified by its mass and distance from its star on the vertical axis. Here are the planets' masses, with the lightest discovered ones shown at the image's bottom, and their masses are approximately, from those like Mercury to the giants, thousands of times heavier than our planet, which are found at the very top. Here, on the horizontal axis, it's the distance to their star that's shown. From those so close that stellar eruptions touch them, to those far from any external heat source. Some would make the inside of your freezer feel like a sauna. And what this diagram shows us indirectly are the limits of our detection methods. Because if there are no points in these regions, that doesn't mean that all existing planets are massive or orbit very close to their star, but simply that for now it's impossible for us to detect relatively light worlds that are far from their star, like Neptune, Uranus, Earth, or Venus, which, as you may have noticed, are outside the clusters of points. Okay, now, let's have some fun with a thought experiment. Imagine that you are an alien searching for other planets, and that, orbiting a star located a few dozen light years from here, you start observing our sun using the best technologies, with no limitations. You would only be able to detect Jupiter, because all the other planets in the solar system would be invisible to you. In other words, if all planetary systems were like ours, we wouldn't have detected any of them so far. Let's add that for these hypothetical extraterrestrials to get their hands, or rather any grasping appendage, on Jupiter by detecting its shadow. When it passes in front of our star, they would have to be patient, because our gas giant takes 12 of our years to orbit the Sun. So they would need to observe our star continuously for more than a decade before seeing Jupiter pass by, then continue observing for another 12 years just to make sure that it really is a huge planet they saw the first time, and not an artifact that might have contaminated their data. So the bad news is that on average, with our current technologies, it's impossible for us to identify systems that are strictly identical to ours. So it's going to be complicated to declare ourselves unique if we can't even detect systems that are identical to ours. The good news is that Jupiter in our system is no small thing. Jupiter is huge. Because while the Sun contains 99.85% of the mass of the system, the gas giant Jupiter is by far the planet that weighs the most on the scale, because it alone weighs more than all the other planets in the solar system combined. By concentrating nearly 2/3 of all the matter that isn't in the Sun, being able to detect Jupiter is therefore a huge breakthrough, especially since this gigantic difference in mass means that it's essentially Jupiter that has shaped and sculpted the architecture of the system. It has regulated the convolutions, the orbits, and has led the dance of the other planets for billions of years. By exaggerating a little, we could almost say that the solar system is our star, plus Jupiter, since those two overshadow everything else, to try to find out if we are truly extraordinary. So we're going to approach the problem differently and try to estimate the number of planetary systems that are similar to ours, starting with the Sun-Jupiter pair. First, to have a solar system, you obviously need a sun. But the Sun isn't just any star. It's a yellow dwarf of spectral type G, a relatively ordinary star, but still far from being among the most common stars in our galaxy, of the roughly 400 stars that are within 30 light-years of us. For example, there are about 20 yellow dwarfs of this type, while there are nearly 285 red dwarfs, small stars that are 2 to 10 times less massive than our Sun, and which, being less hot and less luminous, make up the vast majority of the stars that fill our sky. Brought back to the scale of a structure as vast as our galaxy, stars like our Sun are actually relatively common and account for nearly 10% of the roughly 300 billion stars found there, considering that almost all stars have at least one planet. That still makes 30 billion planetary systems with a Sun-like star at their center. Now let's ask ourselves, among these 30 billion Sun-like stars, how many have a gas giant, comparable in mass and distance to the star, to Jupiter? Well, not many. Today, barely 1 out of 100 stars that we study seems to have a planet with characteristics comparable to Jupiter. Except that this fraction of 1% is expected to increase rapidly because many still go under our radar. For example, it's only been a few years since LON has been able to detect them. While these planets can take dozens of years to orbit their star, remember the example of the extraterrestrials who would be observing us so well? It's estimated that about 10% of Sun-like stars actually have a planet with a mass comparable to Jupiter or Saturn, which could have shaped a system like ours. Except that Jupiter is also unusual because its orbit around the Sun is almost perfectly circular. In fact, nearly 90% of the gas giants we've discovered, orbiting at a good distance from their star like Jupiter does, have very eccentric and elongated orbits. One of the most emblematic cases is that of the HD 8606 system, where LON discovered a giant planet that moves away from and approaches its star in crazy proportions. If you could go into orbit above the cloud tops of this gas giant when it is at the farthest point from its star, you would see the star gradually swell until it reaches 30 times the apparent size of the Sun in the sky. Because this planet has such an eccentric orbit that it completes it in about 100 of our days. The amount of energy it receives from its star, similar to what Earth receives from the Sun, is 800 times greater. So much so that it has been measured when it passes closest to its star. An increase in temperature of more than 500 degrees in just 6 hours. So, of course, the case of this planet is one of the most extreme, and not all of them have orbits with such pronounced eccentricity. But you get the idea. The problem with planetary systems that have giants with elliptical orbits is that, as they move closer to and farther from their star, these giants inevitably end up, over time, destabilizing the orbits of the smaller planets within their system as they pass by. That's why we're pretty sure that all systems with giants of this type are devoid of planets with a mass comparable to Earth's, orbiting in circular paths. And for such planets, it's not trivial not to have a circular orbit. Having an elliptical orbit, that means potentially terrible seasons for the planet, as it gets closer to and farther from its star. So, to sum up, putting all this together, it means that roughly 1 star out of 100 like the Sun must have, like us, a gas giant with an almost perfectly circular orbit. 1 chance in 100. It's not super common, but it still happens fairly often. To give you an idea, it's just a little less likely than getting 3 of a kind in a 5-card poker hand, which reduces the number of Sun-like stars that could host a planetary system like ours from 30 billion to 300 million. In summary, about 1 out of 10 stars is Sun-like, and 1 out of 10 Sun-like stars has a gas giant with a mass similar to Jupiter, and only 1/10 of these planets has an orbit similar to that of our gas giant. That is, much larger than Earth's, and almost circular. So we are part of the cosmic 0.1%, except that there is another remarkable aspect of the solar system. And this peculiarity is only obvious to specialists, because it is not found in the characteristics of any of our planets, but rather in what we cannot see. In the fact that it seems we are missing a planet? Indeed, when we observe stars similar to our Sun, we find that nearly half of them have at least one planet that is a super-Earth or a mini-Neptune, orbiting extremely close to the star. But in our case, that's not true. We don't know why our solar system lacks a super-Earth near the Sun. It's even possible that our system once had one or more planets of this type in the past, but that it ended up plunging into the Sun during the early phases of the solar system's existence. I won't dwell on this now. We'll revisit this terrible story in detail in a future episode. In the meantime, remember this. If we consider that half of the Sun-like stars have lost their super-Earth or never formed one, then we end up with one star out of 2,000 around which orbits a system roughly similar to ours. That is, a planetary system that formed around it, a yellow dwarf star with a Jupiter-type gas giant but without having a super-Earth or a mini-Neptune close to the star. One star out of 2,000 is rare, but it's not exceptional either. You have twice as much chance of coming across a planetary system of this type if you pick a star at random. The odds are like drawing a 4 of a kind in poker, so we're far from a statistical anomaly. If we bring this number to the scale of all the stars in our Milky Way, this rarity actually becomes 150 million planetary systems potentially similar to ours. And our little guessing game stops here. Because it's impossible for us to refine this number beyond the sensitivity limits of our detection tools. Tools that, for now, are still unable to detect Earth-mass planets orbiting at distances similar to the one that separates us from the Sun. Is our solar system the result of a lucky, improbable accident, or of a rather disappointingly common occurrence? The only thing we can say for sure is that, from a purely statistical point of view, if we compare ourselves to the thousands of planetary systems recently discovered, ours does not seem to have any unusual characteristics. Which doesn't necessarily mean it's not exceptional. In fact, when you think about it, couldn't we say the same about all the others, which, in their own way, would surely seem exceptional to us if we could observe them with the same level of detail? We have from our solar system. If I show you a system with 4 small planets near the star and 4 bigger ones much farther away, not sure you'd be impressed by its diversity, but if I tell you that the first one, starting from the star, is a small burning world of rock and metal, without an atmosphere, and as dense as a cannonball, the second one is covered with a thick atmosphere that regularly experiences rain. It's made of sulfuric acid and is almost 100 times heavier than Earth's. A runaway greenhouse effect made it a hellish place. The third planet's surface is 2/3 covered by oceans, while the fourth is not. A small, arid world with deep canyons and a frozen desert, occasionally hit by intense global sandstorms. Farther out in the same system, gas giants often have moons that are just as strange. Some, frozen on the surface, have oceans of liquid water beneath several kilometers of ice. Another, with a dense nitrogen and methane atmosphere, has lakes and rivers of hydrocarbons. Yet another is subject to continuous volcanism and is entirely covered with lava flows and volcanoes. We could go on with the list for a while, so yes, you might say, undoubtedly, this system is exceptional, even though it represents only a tiny sample of the plurality of possible worlds. Our solar system alone is already full of an absolutely mind-blowing diversity when you look at its components in detail. Who knows what we will discover when we have more advanced observation tools, letting us reveal the exact compositions and, for now, mysterious colors of these thousands of new worlds. If Tatooine with its 2 suns, Arrakis and its planetary desert, or Mustafar and its oceans of lava, have long remained worlds of science fiction, confined to the realm of imagination, today in reality, we know of many planets that check all the boxes to be their twin sisters. As for me, I'd be willing to bet the moon, just like those present in our solar system, the worlds evolving in other planetary systems will also, in detail, have an absolutely phenomenal diversity. If, almost 30 years ago, I had claimed without proof that there are systems with 4 Jupiter-like gas planets orbiting very close to their star up there, What if I had described to you a system with 7 planets of similar mass to ours, all clustered tightly around their small red star, to the point of being 6 to 40 times closer than Mercury is to the Sun? You would have died suspected of having inhaled far too much sulfurous atmosphere, or been taken for a crackpot whose ideas went off the rails from staring at the stars for too long. The possibility of the existence of this type of architecture seemed to us at the time highly improbable, out of the ordinary, and therefore abominable, absolutely extraordinary. These systems do exist. They're called 55 Cancri and TRAPPIST-1, and in a sense their norm has become the norm. Because what seems exotic is always built in relation to what we know. And recent discoveries have allowed us to understand that these systems, which several decades ago would have seemed exceptional to us, are actually surprisingly ordinary. And the craziest thing about all this is that this diversity, already exceptional in itself, is obvious to us. Currently, our understanding of these worlds remains incomplete and highly fragmented. And our discoveries are essentially limited to characterizing masses and orbital architectures, and are restricted to massive planets or those very close to their star. When we are able to precisely know the composition of the atmosphere of these thousands of new worlds, will there still be 2 planetary systems that are truly alike? In fact, our solar system may just be a special case among the vast number of possible planetary systems, all of which are, in their own way, just as unique. Maybe even to answer the big question of life beyond our universe. The challenge isn't determining if our system is extraordinary, but understanding how extraordinary it is. All the steps that contributed to giving it the form we know, are they necessary or not for a planet to appear on which life could flourish? In the meantime, until maybe one day we can answer these still open questions, in a future episode, we will see that the discovery of these thousands of different planetary systems has allowed us to reconsider the way they form, and to highlight the existence of world-killer planets, while solving some of the great mysteries surrounding the birth of our solar system. Sean, a big thank you for your help with writing this episode, and also for agreeing to let me take, let's say, a few shortcuts. I was wondering, after this long journey, does it still exist today? Are there clues in our system that, seen from afar, would indicate the presence of a truly habitable planet?
That's a good question. It goes back to the end, to asking the question about the formation of these systems, how they were formed, their origins, and of our system in particular. Since we know about the existence of a habitable planet in our system where we live, and we really want to know the key events that led to the character of our planet. We don't have the final answer yet, and many scientists are still trying to understand how Earth formed. What made it so that we have water on Earth, not too much, but we don't have too much water. We have the right amount, the atmosphere, and everything needed for life. In the end, we think that the solar system formed in a disk of gas and dust around the young sun, and the dominant planet of our system is Jupiter. And we think that even though it is 300 times more massive than our Earth, it formed more quickly, and it influenced the final phases of the gathering of rocky building blocks that made the Earth, so that's pretty convenient. Finally, Jupiter is the planet that had the greatest effect on the formation of the Earth and the fact that it is habitable. And it's also Jupiter, which is the most visible planet from afar, for now the only detectable planet in our system at least.
I suggest we go explore these questions a bit more in a future episode then.
Yes, let's do that, absolutely.
The universe thanks you for spending some time on the billions of worlds around us. Turn on the bell for release notifications and follow me on Insta for Project Behind the Scenes. Otherwise, you'll find the playlist of videos here and in the description. A journey into the origins, which will grow over time, where we'll try to cover the amazing discoveries of recent decades.